So in this very short chapter 6 on the electronic structure of atoms, I'd say about 80% of it is review. So I'm going to go fairly quickly through some of these topics and slow down on the ones that are either new or need more review. As you learned last year, all electromagnetic radiation travels through space as waves, and the wavelength is measured from the trough to trough or crest to crest of a wave. That is what we call the wavelength, and it's symbolized with the Greek letter lambda. Looks kind of like an upside down Y. If you had superhuman vision and could count the number of waves that pass by every second, you would see that a long wavelength has what we call a short, or small is the better word, frequency. And a short wavelength, if you look at these guys in particular, then you would see that more of them will pass by per second if the wavelength is small. So the relationship between those two is an inverse relationship. Big wavelength, small frequency. Small wavelength, big frequency. No matter what the radiation is, though, whether it's visible light that we can see or any of the very long radio waves or the incredibly tiny and powerful gamma rays, they travel through space at the speed of light. The same speed, 3.0 times 10 to the 8th meters per second. So there's a relationship that you can put between wavelength and frequency, and it is an inverse one. If this number, speed of light, stays the same, as wavelength gets smaller, frequency must get larger, and vice versa. Now, the problem with thinking of light as just a wave is that it didn't explain, for example, what they call hot body radiation. And it's not that big of a deal, but basically what we're saying is if you look at some hot metal, starts out cold, it's dark color. And then as it gets hotter and hotter, as you heat it up, it gets redder and redder and redder, and eventually you get to what you would think would be beyond the red wavelength of light being emitted. That's the red hot. Then the next form of radiation that should be appearing would be like infrared. Or if you go the other direction and you get light that would be just beyond the violet, you would have ultraviolet radiation that should start being emitted if you could get the metal super hot. And in fact, that wasn't happening. So one of the ways that this was explained was that Max Planck said that energy is only going to be released or absorbed in little bundles or specific amounts called quanta. Another way to think of this is that when you look at metals, what looks shiny, you can see something that we call the photoelectric effect. Here comes in some radiant energy from the sun. It strikes the surface of a metal, and our human eyeball sees that metals are kind of shiny. But it's not any old type of radiation that comes in. It must be radiation of a specific frequency. If electrons have to be knocked out of an orbit, they have to absorb a very particular bundle of energy. And that bundle of energy is a quantum, and it can be calculated with the equation that you see here. If you know the frequency, and you can utilize Planck's constant, you can multiply frequency times Planck's constant to calculate the energy. And the energy could be energy released when an electron drops from an excited to a lower energy state, or the energy required to bounce an electron out of an atom and provide this photoelectric effect. And the photoelectric effect is something that you can see in this experiment where radiant energy strikes the metal surface, but it's only radiation that was of a particular frequency that could successfully knock loose an electron and have it pass through an electrical external circuit to measure the current. So those two equations, the first one is an inverse proportionality, can be contrasted because this equation is a direct. That number, h, never changes. But if frequency gets larger, then frequency times a constant number should be equal to a larger and larger energy. This is not an inverse relationship. This is a direct one. Big frequency, big energy. So to sum up, little wavelength, big frequency. Big frequency, high energy. And that's why we don't want to stand around by X-rays or gamma rays. Tiny wavelengths, huge frequency, huge amount of energy that can do damage to living tissue. So one of the things you can do is go from the wavelength is equal times frequency equals speed of light, and you can turn that into a frequency which can be multiplied by Planck's constant to give you an energy. In a moment I'm going to break and do some sample exercises, but I think I'm going to power through first on the PowerPoint notes. And another mystery that was solved early on is a replication of the lab that we did last year when we looked at gases inside of gas discharge tubes that were being excited by electrical input. The emitted energy that you saw, if it came from a white light source, would be a continuous rainbow with no breaks in it. Pass energy through a slit, pass it through a prism. I don't see any breaks in the bands of color as the Roy G. Biv, red, orange, yellow, green, blue, indigo, violet light blends smoothly from one into another. That's evidence that there is a wave nature to light. But the particle nature of light can be observed when you look at, say, this very same spectrum that we saw last year. These discrete bands of light that have dark space between them correspond to light being emitted by excited electrons dropping to a lower energy state, emitting light of a particular wavelength, which corresponds to a specific frequency. The wavelength codes for the color our eyeball sees, but the frequency impacts the energy and gives a hint for higher energy electrons would be farther from the nucleus, and as they leap back down to lower energy states, emit more violety purple colors, and lower energy electrons that have traveled a shorter distance from the nucleus, when they release their quanta of energy back to the human eye in the form of light, now we've got longer wavelengths of light that correspond to lower energy, that means closer to the nucleus. So it was this work with light that allowed us to understand that electrons are existing at specific distances from the nucleus. And that's why those emission spectra that you just saw there don't have a continuous blend of colors. They have discrete bands, and those bands correspond to electrons can be here, or maybe over here, but not in between, opening the door to what we know now as quantum mechanics. So Bohr says electrons can only occupy certain orbits that correspond to specific energies. That these electrons that are in the permitted orbits have specific allowed energies, and that these energies aren't going to be radiated from the atom. But energy could be absorbed or emitted in such a way to allow the electron to move from one allowable orbit to another. And that was quantified by the energy equals frequency times Planck's constant. Now trying to keep a little mental picture here. One of the things I just want you guys to see is that there seems to be something to do with 1 over the square of your distance from the nucleus. Nucleus is down here, first energy level, second energy level. Well, 2 squared is 4. Oh, there's something about 1 over 4 here. 3 squared is 9. Now there's something about 1 over 9. Hang on to that, because even though we won't necessarily be doing any calculations for this, I need you to understand qualitatively that the energy absorbed or emitted from the process of an electron bouncing up, that's promotion, or coming back down, that's demotion, is calculated by this equation. This is a constant, and it seems to have something to do with the inverse of the square, the inverse of the final energy level being squared minus the inverse of the initial energy level energy amount being squared, and then you find the difference between those. Remember I just said a second ago 1 over n squared, 1 over n squared. Let's go over here and take a look. And I'm not sure which way these guys are going. But let's say I was jumping from, I don't know. Let's actually wait and do a sample problem on this guy. Ni and Nf are the final minus initial, there it is again, energy levels that the electron's at. If you were at, say, the third energy level in the end, but you started at the second energy level to begin with, it'd be 1 over 9 minus 1 over 4. It's 1 over the square of the number that signifies the energy level. So hopefully you can see, and the negative sign just means the energy that would be, say, released if they were leaping back down. The bigger the difference between these two numbers, then the greater the energy that would be either required to promote or released when an electron is demoted. Now we're really not going to use this Rydberg equation too much. Make sure my guy is working here, and it seems to have shut itself down. One more try here. There we go. So we have this sort of property of light where you can think of it as being kind of like a bundle of energy. But de Broglie said that it could also have wave-like properties. So that was the duality of light. Here is a topic on which I'm going to slow down a little bit. De Broglie proposed that matter could exhibit wave properties. The thing is, when the chunk of matter is big like me, the waves that are generated when I move around are so tiny they're not visible. So what he was able to do was to show that there's a relationship between the mass and the wavelength of the particle that's moving, and they're connected with each other by this Planck's constant. So let's take a look at that. I'm not too worried about this uncertainty principle here, other than to say that we learned last year that the uncertainty principle said you can not ever know for sure where an electron is. That was the chemistry way of describing the location of an electron. The AP chemistry way is that you can, if you're fairly certain of its position, you don't know its momentum. And if you know its momentum more surely, then you're not too sure of its position. And this information down here is not anything that we're going to do calculations with. But when you talk about momentum, it has to do with the mass of an object that's moving at a particular velocity. A Big Mac truck moving down the freeway has way more momentum going for it than, say, a small Prius, even if they're moving at the same speed. So the uncertainty of the whereabouts of an electron could be even greater than the size of the atom itself. And Heisenberg came up with equations that described the location of electrons based upon probabilities of locating it. Now I think that's a good point for me to stop. I'm going to now switch over to a Vodcast part 2 that will be about some sample exercises that you will be encountering. So I'd like to just go directly to that as part of this podcast. And if you look at these concepts of wavelength and frequency, I think you can see fairly quickly the waves that have a smaller wavelength have a greater frequency. And if one of these waves represents visible light and the other infrared radiation, which wave is which? Okay, infrared means beyond red. Red is our longest of our visible light. And then on the other side of red would be infrared. On the other side of violet, which is a smaller wavelength, is the ultraviolet. So if I was going to decide between these two, I'd pick the one with the shorter wavelength to be, say, red wavelength of light, and the one with the longer one to be the infrared wave. And that's the solution that is right here. Oops, sorry, the solution that is right here. The lower wave with the longer wavelength would be infrared radiation. You will be expected to, if given a wavelength, calculate frequency, and if you know frequency, you should be able to calculate energy. This is a rerun from last year. The only thing that's different is, when I give you a wavelength of 589 nanometers, I know I'll be using the equation that has the speed of light in it. The problem is the speed of light is in meters per second. So the original equation was speed of light equals wavelength times frequency. So frequency should be equal to speed of light divided by wavelength. And here we are taking the speed of light, a constant, and dividing it by the wavelength. The problem is the wavelength is in nanometers. So either in a separate step, I would first convert nanometers into meters. 1 nanometer is 10 to the negative 9th meters. If you put in them together, then this nanometer cancels that. This meter cancels that, and you get the classic unit for frequency per second. S to the -1 stands for per second. So be comfortable with reading it that way. Don't forget, these are easy. You just have to make sure the units match up. If I was to calculate the energy of a photon, let's say again, here's that 589 nanometers. The first step is to calculate frequency using this equation. And this is the answer from the previous problem. You leave the frequency in your calculator and you times it by Planck's constant. Notice that Planck's constant is in the strange unit, joule seconds. That will make a second on a denominator get canceled by a second on a numerator, and you end up with an answer in joules. And it's a tiny number, 10 to the -19th joules, for any kind of wavelength that's in the visible range. It's pretty small, but that is how you would calculate the energy of one photon. And if you wanted to figure out how much energy would be given off by a mole of photons, you could multiply it by Avogadro's number and get a certain amount of joules per mole. Again, a rerun problem from our beginning chemistry class. Now I need to insert a little slide from the PowerPoint, and then I think we're almost done except for matter waves. It says, which of the following electronic transitions produces the spectral line having the longest wavelength? So think it through. Long wavelength means small frequency. Small frequency means small energy or smallest energy change. Well, the best way to see that, because here are your transitions, they're saying what if the electron went from the second to the first energy level, or the third to the second, or the fourth to the third? To understand that, we have to go look at figure 16 or 6.14. So the first one is second energy level down to the first. So what we're seeing is here, second energy level down to the first. That would be represented by this distance. And remember, we're taking the 1 over the square of that distance. So let's go back and look at our other choices here. They want to know which one would show, which transition would show the longest wavelength, which means the smallest energy change. So if I look at this distance, that's a pretty big energy change. So it's not that. The second possibility is to go from 3 to 2 or 4 to 3. Let's look at those two together. Here would be the difference in energy change from 3 to 2, and this red line from 4 to 3. So I hope you can see that as the electron shells go farther out from the nucleus, their spacing gets closer together. So an electron jumping from 4 to 3 would have the smallest energy difference, which corresponds to the smallest frequency, which corresponds to a longer wavelength. Okay, so our last question for the night for this Vodcast is, what is the wavelength of an electron moving with a speed of 5.97 times 10 to the 6 meters per second? And they give you the mass of the electron. You could use this matter wave with any object as long as you know its mass. So the equation that we had seen previously, and I'm not going to bounce back there and find that, but it relates wavelength to Planck's constant to the mass of the object to its velocity. And here's where they get a little crazy on you, because they give you a symbol here that looks like frequency, but this time really it is the speed. So I got my Planck's constant. The thing that you have to be careful with is that when you use the Planck's constant, that represents joule seconds. And a joule is if you took a kilogram of mass, spread it out over a square meter, and accelerated it per second per second. I know that sounds funky, but here's what you have to do. Your masses always have to be in kilograms, so make sure that that's done. If ever we give you a problem where they're in grams, just change it to kilograms. Our Planck's constant pops up on top. Here is the mass in kilograms. Here is the velocity in meters per second. And then we got to make sure we cancel out a bunch of junk, so that's where this joule conversion factor comes in. That kilogram will cancel that one. One of these meters will cancel that one. One of these seconds will cancel that one. I think I'm losing, no wait. One of these seconds would cancel one of those. There, I can keep it straight. So by the time we're all done, we end up with everything canceling except for the unit we want to save, which is the unit of meters. So when we crunch all of our numbers back out, we get 1.22 times 10 to the minus 10th meters. And they didn't ask what unit it should be, so you could have just stopped there. But if someone wanted you to put it in nanometers, then that's 10 to the negative 9th meters. And if they wanted you to put it in angstroms, there's 1 times 10 to the 10th angstroms in a meter. So notice that these last two values just differ by a power of 10. You could have just stopped there. The point would be, on the matter waves worksheet, which we will begin tomorrow, you need to make sure that your mass is in kilograms, and you can put in this conversion factor for the joules being equivalent to a kilogram over meter squared per second acceleration. Okay, that's it for tonight's Vodcast, and I will see you guys tomorrow.